My name is Jonas. I'm doing this presentation together with Philipp today, and we will talk about efficient window aggregation with stream slicing. So the idea here is to look into the internals of the Flink windowing operator and to think about how can we make it more efficient by using the stream slicing technique instead of the currently used bucketing approach. And in order to give us all a common idea about how stream slicing works, I want to give you a short introduction with an example on the stream slicing technique so that we all have the same idea about the concept. So let's consider this sliding window we have here. And the nature of a sliding window is this overlap we have between the different window instances. And the idea of slices is now to separate the stream into non-overlapping chunks, our slices, such that we can combine all the windows from the separate slices. So basically, any window we have can be computed from the slices. So let's consider an input stream. We first receive a tuple here with the value 7, which we assign to exactly one slice. We then receive another tuple with the value 5, which we again assign to exactly one slice. And as soon as we receive the second tuple, we can already compute a partial aggregate of those two tuples. Here we use the sum aggregation, so that partial aggregate would be 12. And whenever a new tuple arrives now, we can update this partial aggregate so that we have the partial aggregates of all slides once we are, while we are processing the stream. So the important point here is that we assign each tuple to exactly one slice instead of assigning it to all the buckets of the overlapping windows, and this saves a lot of computation effort. So now when a window ends, there's basically one final aggregation step which remains. Here for the third window, we compute the partial aggregates 18, 11, and 6 to the final result of 35. And this is what the window operator will then output and send to the user. And the important improvement we have here is the aggregate sharing part, which means that for each individual tuple, we have a constant complexity, which is one aggregation step and the assignment to one single slice. And the partial aggregates are then shared among all the overlapping windows. So I want to give you a brief overview about the stream slicing research which we did in the past years. And there are mainly two publications which are the foundation of this talk today. So first of all, in CIKM 2016, we published the paper CATI, Aggregate Sharing for User-Defined Windows, where we mostly focused on the expressiveness of the API and how we can express window semantics with user-defined functions. But we also introduced a technique which allowed to create the slices for the stream on the fly and to aggregate them incrementally. And now on this year's ICDE, we had another paper which was called Scotty Efficient Window Aggregation for Out-of-Order Stream Processing. And here we took a close look on how to address out-of-order processing with stream slicing and also how to address session windows with stream slicing. But before we go into more detail about the stream slicing research and our operators, I hand over to Philipp, who will give you some insights about the bottlenecks in the current Flink windowing operator.
Yeah. Thank you, Jonas. So, I will present you how in Flink the windowing operator is implemented and its main concept. So let's look at the following example query. So we have a sliding window with a length of 1 minute and a slice of 10 seconds. And a really simple windowing function like a sum aggregation. So let's see how Flink processes this window. So in Flink, events get assigned to window buckets. So when the first event arrives with a timestamp of 4 and a value of 3, it gets placed in its corresponding bucket. This bucket has a start timestamp of 0 and an end timestamp of 60, and its aggregated value is now 3. So when the next element arrives in the stream with a timestamp of 15, we have to place it in the first bucket and in the second bucket with a start timestamp of 10. So you already see that we now have to place this element in 2 buckets. When more events arise, for example, this one with a timestamp of 55, we have to place it in in even more buckets. And as soon as an element comes in the stream with a timestamp of 66, we do not have to place it in the first bucket, but in 6 others. So in total, we can say that for sliding windows, we have the window length divided by the slice length. That is the number of buckets we have in total. So for our example query, this accumulates to 6 buckets. That's not so much. However, when we have like a sliding window with a really long window with a small slice, we can get a lot of buckets. Like in this case, we have a window length of 1 day, and we want to get results every 10 seconds, which is, for example, useful for real-time visualization dashboard. We get in the end like 8,600 buckets. So that is a lot of data to store, and all these buckets have a huge overlap. And this causes, for example, that every element in the stream has to be assigned to many windows or many buckets. We have repeated aggregations. So in this case, the sum has to be calculated for every of these buckets. However, when you now think about more complex aggregation functions, this could be really a huge bottleneck. And also we have a high memory consumption. In this case, we have to store 8,000 times the sum value, but when you now think about other aggregation functions or also not incremental aggregation functions, where we really have to store all the values, then this is a high memory consumption. And what is also a problem is that, for example, for session windows, we have to check if we have to merge session windows, and this also results in a high complexity. So Jonas will now talk about how sliding window slicing can improve on this, and how our general architecture is, in this case, on Flink.
Yeah, so let's first look at the input stream, what we get here, and all the architecture I show now is the internals of the windowing operator, so the concepts, how are we operating in Scotty. What we have here as an input stream is a stream of in-order tuples, out-of-order tuples, watermarks, and later on we will also see slice separators. So the first component what we have is a stream slicer, which depending on the timestamps of the in-order tuples creates the slices which are required for all sliding windows and all tumbling windows, and also initial slices for the session windows. However, out-of-order tuples may change the slices for session windows later on. So what we get here is an enriched data stream which has slice separators, but we still need a separate component which we call slice manager, which when we merge sessions or when new sessions come up, creates additional slices or also fuses slices. I will go into a bit more detail about this in a bit. What the slice manager also does is it computes the incremental aggregate based on the tuples it has seen and stores these partial aggregates to the aggregate store component. And then finally, we have a window manager component which receives the watermark, and based on the watermark, the window manager component knows when to retrieve the partial aggregates from the aggregate store and to output the final aggregate for a window. So on the next few slides, I want to go in a bit more detail about the session window processing and why aggregate sharing and stream slicing for session windows makes sense. And then I also want to go into details about the out-of-order handling for session windows. So let's consider a data stream which we have here depicted on the top. We have a lot of tuples and we marked several gaps which have the length 4, 6, 5, 2, and 7. And now we have a set of session windows which have different gap specifications. What we can see here is that for a single session window, aggregate sharing does not make sense because session windows are non-overlapping per definition. However, you often want to have session windows with different gap specifications. For example, if you monitor a taxi, you may want to separate the guests of the taxi driver, but also you want to separate the days, or maybe you want to monitor the car and you want to split the window whenever the car stops at the red light. So that would be concurrent session windows with different gap specifications. And what we can actually see here is that for such scenarios, we can significantly reduce the number of slices, which are the orange bars here, compared to the number of buckets which would be required, which are the yellow bars. So on the next slide, I would like to give you an example about how we handle the out-of-order tuples for session windows. On the top here, you see two initial slices, which are kind of the setup for our scenario, and I want to show you the different cases, what happens when an out-of-order tuple arrives, and how do we update these slices. So the simple case is that we receive an out-of-order tuple, which is the red one in this picture, and this out-of-order tuple is within an existing session. Then we can just do an additional incremental update on our aggregate to make sure the partial aggregate is correct. We can also do an incremental update in the case that a tuple extends the session at its end, or that a tuple extends the session at its beginning. The only condition here is that the gap needs to be large enough still to fulfill the gap requirement. So then we have two more cases which are a bit more tricky. Fortunately, they don't happen too often if you look at practical use cases. So the one case what can happen is that we have to fuse sessions because an out-of-order tuple does not leave a sufficient gap before and after it. In this case, we also fuse the sessions, and we also fuse the slices, and we then have to do one incremental aggregation step to get the correct partial aggregate. And then the final case, what can happen is that an out-of-order tuple arrives, and there is a sufficient gap both before that out-of-order tuple and after that out-of-order tuple. And in this case, the out-of-order tuple is a new session on its own. So then we introduce a new slice, which will only contain the out-of-order tuple, and all the other slices have the same partial aggregates as before. They just change their start and end times respectively. So what I introduced here now on the example with session windows is one case where you have multiple windows running in the same Flink streaming operator. However, if you look in practical use cases, you have many scenarios where you want to use multiple windows over the same data. And here I show you an example where this happens with a fitness tracker and where we also combine the different window types. So first of all, let's say we want to have a daily report which shows us how we performed over each day. That would be a tumbling window of one day. Then we may want to have a live dashboard where we can follow our activity in the last hour. So for that, we want to have a sliding window with a duration of 1 hour, and we want to have frequent updates, so we say the slide step is 1 second. And finally, we want to split our periods of activity. So for that, we say that we take a session window which times out after we have 1 minute of inactivity. So all of you would now be timed out because you are sitting for 1 minute of activity, but you would be able to see how did you perform on the way to the conference this morning, because then you moved. And all these three windows could now operate based on the same slices and share the partial aggregate which we compute, and it is not necessary to replicate the stream or to have the overhead of assigning windows to a lot of buckets. And I want to give you some performance numbers which actually show the effect of this. And here on the x-axis, we have the number of concurrent windows. On the y-axis, we have the throughput. And what you can clearly see, the middle line is the bucket solution. And since we have a 1 to n assignment from tuples to all the overlapping buckets, the throughput of the solution decreases linearly if we increase the number of concurrent windows. And as you can see for the Scotty Lazy and Scotty Eager solutions, the slicing techniques do not have this issue because we always have this 1-to-1 assignment. And for a high throughput data stream, the management overhead for the tuples is negligibly for the windows is negligibly small compared to addressing all the tuples which we process. And for comparison, for those who know it, we also have the aggregate 3 solution flat fed here in the figure. So one more thing I want to highlight on the performance is that out-of-order tuples are processed as efficient as in-order tuples because the assignment does not make a difference between in-order and out-of-order tuples, so both buckets and our solution perform linearly when we increase the fraction of out-of-order tuples. So at this point, I want to hand over to Philipp again, and he will give you some more insights about another feature, which are runtime dynamic windows.
Yeah, thank you. So, as Jonas already mentioned, we can now combine multiple windows in one operator. So we then thought, okay, this could be really beneficial for many use cases. For example, when you have the following thing, you have 2 streams. One is the event stream, and you have a second stream with window definitions. That can, on the one hand side, be the normal window definitions like you have in Flink currently, or a window definition for only one window aggregation. So you say, okay, I want to have a window aggregation over my day to the Flink forward day and only aggregate maybe the user counts at a ticket shop or so. So both streams are consumed by a dynamic window operator now, and we can at runtime change the window definition and add new windows to the window operator, and then get the output stream of the window and the final aggregate. So we think that's cool. This is really interesting for real-time visualizations, where a user, for example, can change window definitions at runtime. And for API, it could, for example, look like the following, really similar to a CoFlap operator, where we have a dynamic window and the window definition stream, and then some kinds of aggregation function. So this is just another feature we can enable with the Scotty technique. However, this is just a research prototype. And as you know, from research to production is always a hard way. So, and we also have to do still a lot of to-dos in our code and things we have to improve on. So first is that we have to implement a fault-tolerant and solution, and also take the state management of Flink into account, because just for our research prototype, we skipped that part. And another really important thing is state migration. So when you think about, you have a running Flink application with the bucket window operator, and when you now would want to migrate on a new Flink version which uses our Scotty approach, you have the problem that you cannot split the pre-aggregated buckets into slices. That is just not possible. So there's also no easy solution for migrating from a bucket window operator to a slicing window operator. Another thing is that for production use, we definitely need more testing on our solution, and to get it to a production-ready quality. Besides this, there's also the question how we can expose the multi-window and dynamic window functionality to a user. And the question how usable this really is and how many users would benefit from this, because that would basically be an API change. And then, So to wrap up, you saw the really interesting Scotty features, how Flink could benefit from that with new features and also better performance. And there is a Jira issue which mainly focus on the performance improvements for sliding windows. Currently, Uber is taking over some of this work to bring this to production. However, when you are interested in this, it would be really nice when you comment on the issue or show your interest, and so we can get a bit more traction. Thank you very much.
Thank you, guys. Are there any questions from the audience? Hi, I'm Jonathan. We heard in the keynote this morning about maybe unifying a unified API for stream and batch processing. Do you think any of these things could also be implemented as batch processing?
I mean, the general question is what would be the batch processing pendant to a window operator. Basically, the window operator is one of the things which really differentiates batch processing from stream processing. And we basically have a full replacement of the window operator. So what you could do on a batch engine is that you say you want to derive windows over certain timestamps you have in your data. And then, of course, you could use our operator again.
If you would use these slices, you would need to find a way to merge those slices together to get the final aggregate right. Is that then something the user would have to implement, like a merge function for different aggregates, or is that something you can implement in a smart way?
Yeah, what happens right now in Flink is that there is a set of predefined aggregations, like a sum. And of course, for those, we use the functions which are already there and predefined. So for those, you don't have to do anything. Still, you can use the user-defined aggregation functions as well, which may be more complex. And then you use the standard reduced function, which is provided by Flink. There are also extensions which make it possible to have pre-computations for order-dependent aggregates and these things, but we left this out of the presentation because of the limited time. But there are solutions for this as well.
Thank you very much, guys.